Hello everybody. After completing the single phase AC circuits, I start today the three phase AC circuits. So in this chapter, three phase AC circuits, our contents is this: necessity and advantage of three phase systems, generation of three phase power, definition of phase sequence, balanced supply and balanced load, relationship between the line and phase values of balanced star and delta connections, which are the two possible three phase connections. Then we will do power in balanced three phase circuits, how to measure the power using the wattmeter, that is measurement of power by two wattmeter methods, then determination of power factor using the wattmeter readings. And there are some few example problems from the old question papers of our university VTU. Now these are my educational objectives. So here, after inventing the single phase AC supply, so normally the AC current was first used for heating the filament of an electric lamp. So for this purpose the single phase AC supply was sufficient. But when the DC motors are try to replace by AC motors, okay, which should operate on AC supply, it was found that the single phase AC supply was not very satisfactory for this application. The reason is the single phase supply will not produce a rotating magnetic field. So the single phase induction motor, the most commonly used, was not self starting. So that is why the invention of three phase supply has to come out. Okay. So it was so to convert the single phase induction motor into a self starting, we used to use an auxiliary winding which is used for the starting purpose. So to avoid that auxiliary winding, the additional winding, okay, we invented the three phase induction motors. So it was found that by using two separate windings with a current differing in phase by 90 degrees or three windings with currents differing in phase by 120 degrees, I can make the induction motor a self starting, and it will give us a better efficiency and power factor also. Okay. Therefore, when the three phase induction motors are invented, so along with that the three phase supply or three phase AC circuits were also invented. Okay. The system utilizing two windings is referred to as two phase system, and that winding, that system which utilizes three windings is referred to as three phase systems. So in two phase systems the two windings are separated, okay, separated by 90 degrees. The spacing between the windings are 90 degrees, whereas in three phase systems the windings or the coils what you have, they are displaced by 120 degrees with a space difference. In coming slides I will be showing you the phase difference between the space difference between the positioning of the coils to get a three phase supply. See, what are the advantage of three phase systems? If you see the first advantage, the three phase transmission lines require much less conductor material. Since the phasor sum of currents in all the phases is 0, there is a substantial saving in eliminating the return conductor. If you see a single phase supply, there will be a line and a neutral. The neutral will take the current, okay, in the reverse direction compared to the line. So in three phase system this neutral wire is not necessary, as under balanced conditions the sum of the three currents is equal to 0 in. There are some circuit three phase three wire system we call them, okay, where whether the system is balanced or not, the sum of the three currents will be always equal to 0. Therefore the return conductor is not necessary. So this makes a reduction in the conductor material. Therefore we say three phase system requires much less conductor material. So if we see the second advantage, for a given frame size a three phase machine gives a higher output, okay, it gives us higher output than a single phase machine. Okay. Here machine is just normally a motor only. The power in a single phase system pulsates at twice the line frequency. However, the sum of powers in the three phase in a three phase system remains constant. Okay. So the power is not a pulsating power. Therefore a three phase motor develops a uniform torque, whereas a single phase motor develops pulsating torque. So because of this pulsating torque, the single phase motors are not self starting, whereas a 3-phase motor is developing a uniform torque, therefore they are self starting. If you see the fourth advantage, since there is a since the 3-phase supply can generate a rotating magnetic field, okay, generate a rotating field, the 3-phase induction motor all self starting, okay. This rotating magnetic field what you have, it will have a constant magnitude but rotates at a constant speed also, okay. So the 3-phase system can be used to supply domestic as well as industrial power or commercial power you can call. So instead of using a three single phase systems, I can use a 3-phase system. I can supply a single phase load also using the 3-phase system, as well as 3-phase loads also can be supplied. So that is an added advantage compared to single phase systems. The voltage regulation in 3-phase system is better than that in single phase supply, okay. So normally in a 3-phase systems we use a double subscript notation. See, for this voltages we will be using a notation as VAB. A represents one terminal and B represents the other terminal of the coil, okay. So VAB represents the voltage of a point A with respect to point B. It is equivalent to plus minus sign, okay. So whichever potential is higher, I will put a plus sign there, and minus, that is lower potential, I will put a minus sign. So instead of writing that plus minus, I will be representing the voltages as V and VAB. There are two suffixes here, that is why it is called as double subscript notation, okay. So it is equivalent to marking plus or minus. So either one you can use, either plus or minus or AB, okay. Generally in 3-phase circuits we will go for double subscript notation than the single subscript notation, okay. Now for the currents, we define a current direction AB as the current flow from A to B by a direct path. So it is not necessary to give again the direction of the current flow by an arrow. It is understood current flow from A to B. Here potential VAB, A is higher potential than B. So A is positive, B is negative. So for voltage also it is not necessary to give plus minus sign. It is always understood whatever the first subscript you have, that will be at higher potential, the second one will be at the lower potential. So when you say VAB, A is higher potential than B, okay. When IAB, we say the current flow from I to B, higher potential to lower potential point. See, concept of 3-phase voltages, if I take this, a 3-phase voltage system requires 3 single phase EMFs having the same amplitude and frequency but phase displaced by 120 degrees. The phasors are assumed to be rotating in the counterclockwise direction at an angular velocity of omega. If you see here, I have just shown you 3 voltage sources, okay, ER, EY and EB. Here I have taken R dash as the terminals, therefore the corresponding voltage, induced voltage, I represent it as ER dash. Similarly EYY dash, EBB dash. So I have used this double subscript notation here to represent the voltage magnitudes. Now see, if you see here, in the space of 360 degrees, the voltages are displaced symmetrically. The angle between any two voltages, if you take, it will be 120. R and Y, they are displaced by 120 degrees, Y and B, they are displaced by 120, and B and R are also displaced by 120. Now these angles are measured in this direction, okay, in this direction, counterclockwise direction what we call. So if you see the direction of rotation, now the R vector will be always moving in the first and then followed by Y, that followed by B. So here the length of each phasor represents the maximum value what is induced, okay, what is the maximum value of the voltage. So 3 EMFs will have equal amplitudes, that is what I said, okay. A 3-phase system, all 3 coils will have equal amount of maximum value of the EMF induced, and depending on the position of the coil in the space, okay, there will be a instantaneous voltage for each of the phase. Even the instantaneous values also will differ in phase by 120 degrees, because this 120 degree what you have, the phase difference between the coils, it is fixed one, Okay. So, the time diagram generating the projection of each phasor onto the vertical line which I have not shown here. Okay. I could have drawn this horizontal reference axis along the red r vector, and a vertical line I could have drawn here. I have not drawn that. Okay. So, if I take the vertical axis, the projection of that vectors along the vertical axis will give us again the instantaneous values. If these instantaneous values are plotted, I will be getting 3 sine waves. Okay. Now, you can see the red wave, because it is coinciding with x axis or the reference axis, it starts from 0. Okay. So, it starts from 0. As this vector is rotated in the coordinate system, the voltage induced will follow a sine curve with a peak value of Em, capital value of Em. Okay. This is the peak value, and this r phase voltage as represented by Er of t here. Okay. The lower case says it is the instantaneous value, upper case letters what I am using represents the maximum value or RMS values. Okay. Or you can say these are the vectors, maximum value. So, instantaneous value, peak value, like that. Now, here if you see this, there is a phase difference of 120 degrees between r phase and y phase. That is, after the r vector moves by 120 in the counterclockwise direction, y coincides with the horizontal axis, and then its instantaneous value becomes 0. Okay. So, by the time the r vector moves by 120, the b phase vector what you have, it also moved by 60 degrees, no sorry, not 120, it also moves by 120 degrees. But the moment the r vector moves by 60 degrees in the counterclockwise direction, the b phase vector also moves by 60 degrees in the same direction, then it coincides with the negative real axis, therefore, its value will be 0 here. Okay. This is 0, this is 60, and the maximum value occurs at 90, and this is again 120, this value will be 180 degrees. Okay. Now, if you see here this time diagram, when r phase vector has a 0 value, the b phase and y phase vectors has some value of EMF induced in them. The instantaneous values of the voltages induced in the y phase and b phase, if you see, they are equal. Okay. 0.866 times E maximum, this is also 0.866 times E maximum, but this projection, that is the b phase voltage projection, will be on the positive axis and y phase projection will be on the negative axis. That you can see here. Okay. I have my vertical line passing through this origin vertically like this. So, for this corresponding position, the projection of the E phase vector on the vertical line is 0, and the B phase vector, it is 0.866. Okay. So, as this vector moves, the value of the projection will keep on decreasing. So, when it moves by 60 degrees, it becomes 0. By the time it is decreasing, the E phase Y phase vector, it will be approaching the vertical axis. Okay. When it is moves by 60, this vector also moves by 60 degrees. So, the position of this vector will go to the 4th quadrant, where the real component is positive and imaginary component is negative. So, by the time this rotates by 120 degrees, this takes position of B, and B takes the position of Y, Y takes the position of R. Okay. That you can see in this diagram. Okay. When R reaches by 120 degrees, Y is taking the position. So, Y phase becoming 0. Okay. So, there is a sequence in which these voltages are attaining the 0 values. Okay. 0, 0, right. 0, it is like this, increasing. So, now it is starting from 0. Okay. It is starting from 0. So, next I have Y phase, then next I have B phase. Okay. So, this is a phase sequence, you can see here, R, Y, B, R, Y, B, next then again R, Y, B, like that. Okay. So, the positive maximum value first occurs for R phase, and then in succession for Y phase and B phase. So, the sequence in which these windings or the phases, what you call R phase, Y phase and B phase, reaches their maximum values, I can call that as the phase sequence. Okay. I can also follow the 0 values, but see, there is a 0, it will be a problem. Okay. Why? Because R, Y, Ry here, there is 120 degrees difference, but when you see this, there is a 60 degree, okay, so it is a 60 degree. Now if you compare the time taken by these voltages to reach 0 value and increase in the positive direction, then you can see this, first R, then Y, it is 0 here, increasing positive way. Before that time what you have, the Y phase is negative, okay. Now in this B phase, the value, it is decreasing from a maximum, a value of 0.86 at t is equal to 0 and approaching 0. So I cannot consider this when I take the 0 values, okay. I should take 0, it should reach 0 and then increase in the positive direction. Therefore R phase is reaching 0 here when t is equal to 0, increasing the positive way. Y, it is reaching 0 here, increasing in the positive direction, that is the positive half cycle. B, it is 0 here, increase in the positive direction. So if you see the 0 points, first R, then Y, then B. Same way, if you take the maximum values also, positive half cycles, R is reaching the maximum value first, followed by Y, followed by B. Therefore the phase sequence is RYB. Now the phase sequence, how you get, it all depends upon the how you arrange the windings or the coils, R phase coil, Y phase coil and B phase coil in the magnetic field, okay. So because of the phase difference of 120, we say here, see now first R is becoming 0 here or maximum here, after an angular difference of 120 degrees, Y is becoming maximum. So now Y is following R, therefore I say Y lags the phase R, phase Y lags phase R by 120 or 1/3 of a cycle. Just remember it as 120 and all, it is not necessary to bother about this. Now this 1/3 of a cycle is expressed as 120 degrees only, and the B phase is lagging Y phase by 120 because the angular difference between the positive maximum of Y phase and positive maximum of B phase will be 120 degrees. So if you see the phase difference, Y is lagging behind R by 120, B is lagging behind Y by 120, therefore there is a angular difference of 120 plus 120, 240 degrees with respect to R and B phases. Therefore you can also say that Y lags R by 120, B lags R by 120 plus 120, 240 degrees. So for the three phase voltage system voltages is said to have a phase order or a phase sequence RYB, R followed by Y followed by B, okay. The phase order of three phase voltage system is very important because depending on this direction, this phase sequence, I have the direction of rotation for the induction motor. With this phase sequence, if the motor rotates in the clockwise direction with a reverse phase sequence, that is RBY, I will get the motor direction in the otherwise, okay, other way. That is, if this case it is rotating in the clockwise direction with the phase sequence of RBY, the induction motor rotate in the counterclockwise direction. So the direction of rotation will change, okay. So therefore in the case of three phase induction motors or three phase system, this RYB is very important. So in the three phase system, if I take sum of the three phase EMFs, okay, ER, EY, EB, these are the instantaneous values, okay, and in terms of RMS values we write it like this, ER, EY, EB is equal to 0. This condition, that is sum of the three voltages at all instants equal to 0, holds good for three phase system, okay. But here to verify that, I have to take one of the voltages as a reference. Now I am sorry, here I have not taken this, I should made this as a R, I have written it as A. Kindly read this as R, ER as a reference phasor. With respect to ER as reference, I have the two other voltages instantaneous values as EY. ER is EM sin omega t, okay. Just now we saw that the vectors rotated with a maximum value of EM is giving us a sine curves with a phase difference of 120 degrees between them, okay. So therefore EY is equals to EM sine of omega t minus 120, there is a phase difference of 120 here. Ey lagging behind Er by 120, that minus sign represents that, and Eb is Em sin omega t minus 240, again the minus signs says it lags behind Er by 240. Okay, lags behind means I am measuring in the counterclockwise direction here, okay, whereas that is the rotation of the vectors, it has to move by 240 degrees to take that position of R. Okay. Now you can also say that instead of writing minus 240, I can also say Em sin omega t plus 120. Okay. So one angle is measured in the clockwise direction, this angle is measured in the counterclockwise direction. Okay. So minus 120 plus 120 and minus 240 will give us the same meaning, that is the phase difference between R and B. Now how to generate these three voltages? If you see the three coils RR dash, YY dash and BB dash wound on a rotor, okay, and they have a space displacement of 120 degrees, rotor will be cylindrical. So you can arrange these coils on a cylindrical, okay, cylinder, okay, cylinder makes 360 degrees. If you arrange them in such a way that between the start of these coils you have a phase difference of 120, definitely the induced voltages in the coils will have a phase difference of 120 degrees between them at any instant. Okay. The rotor is rotated in counterclockwise direction in a uniform magnetic field with a uniform angular velocity of omega. This is not W, kindly read it as omega. Okay. A sinusoidal EMF is generated in each coil. Because of the space displacement of the coils, after 1/3 cycle of rotation, coil YY dash occupies the same position of the coil RR dash. Okay. So here I gave you a small diagram. You can see I have a R coil, Y coil and B coil. Okay. See, I have to give an yellow color only because generally we represent the phases as red, blue and yellow. Okay. There is other notation also we have. You can use ABC or UVW like that. Okay. So any notation will be okay, but normally universally followed notations are RYB, ABC and UVW. So therefore I just selected RYB, okay, so that I can give a meaning of R for red, Y for yellow, B for blue. So I use the same colors to represent the coils here. The EMF in coil YY lags behind the EMF in coil RR dash by 120 degrees. If you see, observe this winding, these coils, you can see we have R here and R dash. Okay, this is the position of the R coil. If you see Y, this is Y, okay, and this is Y dash. Y dash are appearing diametrically opposite, but I am interested in the positions of these coils, okay, measured between the startings. When I say R dash, R is the starting, R dash is the end, finish of the coil. So R and Y, they are displaced by 120 degrees, I marked it here 120 degrees. Similarly Y and B, where B is the start of the B phase, this also has 120 degrees, and then B and R, these are also 120 degrees. Okay. So therefore this space adjustment what you have 120 degrees you have to maintain. Okay. So then the EMFs induced will also have a phase difference of 120 degrees, because these coils are identical in terms of cross section or area of the coil or the number of turns. All the three coils will have equal amount of voltage induced, equal amount of maximum value of voltage induced in them. Okay. But the instant at which the voltages induced voltages are maximum, that differs. Okay. Now it is also possible, now I said here in the previous slide what I have shown here, this of course what side you are seeing here, the coils are rotated, okay, in the magnetic field. Now I need to collect the voltage what is induced by the coils. Therefore as the coils are rotated, it is difficult to collect the current or voltages induced in the coils, okay, which are rotated. For this I need to use slip rings. Okay. The slip rings are rings which are connected to the ends of the coils, and along with the coils the rings also will rotate, and at the surface of the rings I will be placing brushes which will make contact with the rings, and I need to draw the current through the brushes. Okay. the number of brushes, the size of brush, all will depend upon the current in the coil. As the voltage is becoming larger, you need to have sufficient spacing between the rings what you are placing, and the rings should be insulated properly. So it is difficult to maintain that insulation or provide more amount of insulation with this rings as the voltage increases. Therefore, the best method what we do is, instead of rotating the coils, we keep the coil stationary, okay, we keep the coil stationary and we rotate the magnetic field. Now you can see here I have just done a 2-pole magnet here, permanent magnet, and I can also use, instead of using a permanent magnet, I can also use a coil wound on an iron core, okay, working as a magnet, or I can have construct electromagnetic poles which produce the magnetism, that is the magnetic field, when the current passing through the coils, okay. So depending on the current direction, I will be getting the polarity for the poles. Here I am using just one magnet, permanent magnet, north pole and south pole. This S could have been in the corner of this pole, okay, magnet. Now this magnet is rotated in the clockwise direction. Now here the coils, still I have represented them to be on a circle only, because the part of the machine where I will be placing them will also have a circular opening like this, and the conductors are distributed on the periphery. So conductors remain stationary, the magnetic field is moving, so again there will be change in the flux linkages, therefore there will be voltages induced which also have the same amount of phase sequence as that of the previous method, okay. Now here, because of the coils are remaining stationary, it is not necessary for us to use any slip rings. Directly we can collect, okay, the current without the slip rings. That is the advantage, okay. So most of the alternators what I use in generating the electrical power in the power stations will use this kind of structure. Of course they don't use 2 poles, there will be more number of poles, okay, depending on the type of the machine, okay. Now the 3 phases of the 3-phase system can be represented independently. Assume an EMF to be positive when acting from finish to start of the phase winding. The 3 EMFs can be represented by arrows ER, EY and EB, okay. These 3 EMFs can be connected to a 3 respective loads L1, L2 and L3. This arrangement necessitates 6 line conductors, okay, 6 line conductors. This arrangement I am showing you in the next slide, okay. Depending on the interconnected system, fine, I will just, I think the slide I missed it here, I will show you what I am doing now, okay. I have, this is R phase, ER, this is how I represent the voltage. This is the start and this is the finish. Similarly, I have the other 2, this is EY, this is finish, this is the start. Similarly, I have EB, the instantaneous voltage induced, it is positive in this direction, so start, finish. So this is one conductor, this is the second conductor where I am connecting this to a load L1. So this is 1, 2. Similarly, third conductor will be connected to L2 and the current will flow back through fourth conductor, and then I have the fifth conductor and a sixth conductor carrying current to the load 3. This is fifth one, sixth one, okay. So these are the methods of connecting or supplying, okay. Now what happens here, you can see there is no, these are all 3-phase systems, fine. I have not interconnected them, right, and here also the loads are there, I am not interconnecting. So each one I can consider to be a single phase system, okay. This is a single phase system, this one is a second single phase system, this is the third single phase system. Now the current what this L1 draw depends only on ER, L2 depends only on EY, L3 depends only on EB. There is no interconnection at all. Okay. So this arrangement where I am generating 3 voltages, but these 3 voltages are supplying 3 individual loads through 6 conductors, 1, 2, 3, 4, 5 and 6. Okay. So this is what this slide means. So depending on the interconnection of windings, I can get 2 types of connections, 3-phase systems, that is star or Y connection. Okay. The second one is delta or mesh connection. Fine. So if I see the 3-phase loads, 3-phase voltage system can be used for the following in the following manner at the consumer end. 3 phases can be used independent of each other, supplying power to different loads. That is what I have shown you on the board. Each load gets power from single phase. The system is adopted for domestic power supplies, but generally, of course, I will come to that what I am about to tell you later after finishing of this. The loads are connected to form a 3-phase system. The loads, that is impedances Z1, Z2, Z3 can be either star connected or delta connected. When you interconnect the loads along with the supply, then I will be getting a 3-phase power system. Okay, 3-phase supply, supplying power to a 3-phase load. So that means I need to interconnect these supplies separately and load separately and supply them through the reduced number of wires. Okay, I can do that. See, in the 3-phase load, if all the 3 impedances are equal, both in resistive as well as in reactive parts, the load is said to be balanced. Now I have shown you here, if you give a balanced load, okay, to a balanced load, if you give a balanced 3-phase supply, the currents also will be balanced. See, this is Z1, Z2, Z3. Okay. Now if I take these values to be all different, either in magnitude or angle, okay, then I call the load as an unbalanced load, right, unbalanced load. So that is what I am telling you. I am using a single phase supply here, I am using one heater, okay, L2 I have connected to a refrigerator and L3 is a washing machine. All these 3 are different, they are supplied in a different way. Okay, R phase is connected to that, Y phase is connected to this, B phase is connected to washing machine and all. So such case what happens, this will draw some current from supply, this will draw a different current, then this washing machine also draw a different current. The currents are not identical, okay, they are not equal in magnitude. And what is the angle between the voltage ER and the current IR? It all depends upon the angle of this L1, okay, angle of the load. Now this load can have an impedance of Z1 in magnitude and an angle of theta 1. So it will be, current will be lagging behind the voltage by theta 1, in this case it is by theta 2, in this case it is theta 3. If all 3 loads have common impedance, that is same amount of impedance and in magnitude and in angle also, then I say the loads, I can say the loads are balanced. Okay. Then I can, of course, even in unbalanced case also I can connect them to be a star or delta, does not matter, but I do not call the load as a balanced load. If all the 3 impedances, what I am showing here, a star connection and a delta connection, if Z1 is equal to Z2 is equal to Z3 both in magnitude and angle, then this becomes a balanced star connected system. Similarly, in this case, as I am seeing this, the shape of this connection is the Greek letter delta, therefore I call this as a delta connected load. So delta connected load forms a closed loop, you can see here, okay, this is a closed loop. And again here also, if Z1 is equal to Z2 is equal to Z3 both in magnitude and angle, then I call this as a balanced delta connected load. Now here I will come to this star connected 3-phase system. So in connecting the star connected 3-phase system, what I am doing, you kindly observe this. I have taken the diagram what I have taken here, ER, R phase, Y phase and B phase, fine. Now I will show you on the board how to connect these 3 single phase systems what I have drawn to 3-phase system. What I do is, in connecting the star connection, I will just remove this, okay, I remove this line, I remove the 4th line and I remove the second conductor also, okay, second conductor. Now what I do is, I will be connecting the finish of the first winding, okay, finish of the first winding to the finish of the second winding, and the finish of the second winding will be connected to the junction of the first two finishes. This is point, okay, like this. Now in doing so, what I am doing, I am eliminating the conductor 2, conductor 4 and conductor 6, right. So 3 conductors are eliminated, fine. Similarly on the load sides also, I will be connecting all the second terminals together, okay. Now see here, joining together the 3 finishes R dash, Y dash and B dash, I got this connection, okay, interconnected system. Similarly load terminals are also connected, fine. Now I just show you a connection between these 2 points. This is the common point for the load and this is the common point for the supply, okay. I call this as N here and I call this as M, what I indicated on the slide, okay. So I can also connect a wire between N and M, okay. This is called 3-phase 4-wire star connected system. Star connected system. I just interconnected the phases to reduce the number of conductors, therefore I will be saving the current conductor material, okay. Now here, so this arrangement what I did can also be represented this way, okay, 4-wire 3-phase system, because I am using 1, 2, 3, 4, okay, 1, 2, 3 and 4, fine. So what I am eliminating, second and sixth conductor, right. Now you see one more point here, if this L1, L2, L3, L1 is equals to L2 is equal to L3, that is all the 3 loads are identical, okay, or you can say the impedance of the loads Z1 is L1 is Z, L2 is also Z and L3 is also Z, okay, all 3 impedances are equal, then I call it as a balanced load. The balanced loads, because the loads are equal, they carry the same amount of current IR, okay, IY and IB, they draw the same amount of current from the 3 phases, okay, same current with the same amount of maximum values, and as this voltage is having a phase difference of 120 degrees, the currents also will have the phase difference of 120 degrees among them, okay. There may be a phase angle difference between the corresponding phase voltage and phase current, but these currents are also between them, they will have a phase difference of 120 degrees. Therefore when the load is balanced, supply is balanced, so all the 3 currents what you have, they have same amount of currents, okay, and they have a phase difference of 120 degrees between them, they have the same maximum value. So this is an advantage here, because I know load is balanced, supply is also balanced, therefore it is sufficient for me to calculate current in any one line. So the other 2 currents we can automatically write down, because the magnitudes are same and the phase angle difference between those currents is 120 degrees, okay. Now this connection, when you put, it looks like Y, therefore I can also call it as Y connection or star connection, okay. In junction N what you have, this is called as neutral, okay, it is called as a neutral point, and the M here I don't call it as a neutral, but I call it as the star point of the load, okay. Now I will come to the same connection now. So before going to the delta connection, I like to finish off this. I told you IR, IY and IB, let us say IR has a maximum value of Im sine of omega t, this is the expression for current IR. So IY will have a current of Im sine of omega t lags behind IR by 120 degrees, Similarly, IB will be Im sin omega t lagging behind current IR by 240 degrees. So, okay, or I can also write this as Im sin of omega t plus 120. Now I will come to this point M, okay. IR is coming to point M, IY is coming to point M, and IB is also coming to point M, okay, as per the directions. All the three currents will meet here and there will be a current flow of IMN, okay, IMN. So if we apply Kirchhoff's current law at the point M, then I can write here IMN is equals to IR plus IY plus IB. All these currents has a maximum value of Im, then it is sin omega t, okay. IR is sin omega t plus sin of omega t minus 120 plus sin of omega t plus 120 or minus 240 degrees, whatever you want you can write there, okay. Adding all, okay, so I will be getting here a resultant as 0, okay. That means Imn, the value of the current is 0. When this will happen? When the three currents drawn by the loads satisfy this condition. What do you mean by that? The currents are all balanced. That happens only under this condition, that is all the three loads have equal amount of impedance, okay. That means under balanced load condition the current between M and N will be 0. Therefore, for balanced loads it is not necessary to connect these two points together, okay. Even if you connect it, it is not carrying current. So when there is no return current, so it is not necessary for me to connect that. Therefore, when I remove this wire as it is not carrying current, I will be getting 1, 2 or 3, only 3 conductors, then I call that a 3-phase 3-wire star connected system, okay. If it is unbalanced case, okay, if it is unbalanced case, then by connecting M to N I can have a return current. Even the loads are unbalanced, still it is possible for me to have a 3-phase 3-wire system, but that case the load is unbalanced, therefore I do not call the system as a balanced system, okay. Because the 4th wire is not available between the M and N, that case also there is no current because I am not connecting, therefore there will not be any current from M to N. But under that condition the voltage at M will be different compared to the voltage in N. N usually will have a voltage of 0, M will have slightly larger voltage, okay. For the first semester basic level that is not sufficient. Simply remember this, if the load is unbalanced, okay, the point M and N will be at different potential. If the load is balanced, okay, that means supply is balanced as well as the load is balanced, then M and N will be at same potential, though even if you connect the 2 points, no current will flow through them, okay. This is what the 2 slides now will show that, okay. This is what all are talked about this 3-phase connection, 3-phase 3-wire connection system. Now the 3-phase star connected system, 3-wire system can also be represented like this, okay. Now here I have shown you a generator, this is where I am generating the 3-phase voltages, right, and these are the terminals of the generator. Then this is a 3-phase load, R to R phase, Y to Y phase, B to B phase. So this is okay because it is a load, whatever way you want you can connect that, okay. So but I just shown you here the LO phase of the load is connected to LA phase like that, and R, Y, B what I am shown here is are the terminals of the load. So there is a transmission line conductors, okay, between the generator and the load. This is, see, I have taken Z here, Z, Z. So this is what you have balanced system, okay, that is why I mentioned here balanced load, and this is a generator. Normally we generate only balanced voltages here, okay, and these are the transmission lines. So we need, so this is what you have 3 phases, okay, 3 phases, 3 loads. Therefore it is a 3-phase system and all the 3 impedances are balanced. therefore it is a balanced 3-phase system, right, and I am using only 3 conductors to connect the load to the supply, therefore it is 3-phase 3-wire balanced star connected system. It is also possible to have unbalanced 3-phase system. Okay. Now suppose I have a residential locality where I have around say 10 number of houses, all the houses 10 houses, they won't have the same amount of power rating. Okay. One house will be about on 3 floors, the other one will be 2 floors, the other one has only a single bedroom house. So depending on the size of the house, my load will be there. Okay. So I need to draw that amount of, suppose say I have 10 houses, so out of the 10, 3 are 3 floor houses and 2 are 2 floor houses, and the remaining 6 what you have, okay, say 5 what you have, they are all ground floor houses. Okay, 1 floor only they have. So that means less number of rooms in the ground floor and we can have more number of in the 3-4 building, right. Suppose say if the 3 different floors are there and 3 different families are residing in that, then generally what happens, the owner will draw a 3-phase supply, so that he will be giving first phase to first floor, ground floor, second phase to second floor, third phase to third floor, like that. But in such case what happens, one of the houses may have more number of electronic gadgets or electrical gadgets and all, so the other house has nothing. So that case the load in the first floor will be lesser compared to the ground floor, like that, right. So now whatever the power it is coming, the feeder lines what we call, I will be getting a 3-phase feeder lines from the transformer. So when different houses are there, some houses are taking a 3-phase supply, some houses are drawing a single phase supply. Okay. So all these houses in the same locality are connected to the same lines. Therefore you may have a load balanced or unbalanced, but I have a 3-phase system, right. When the loads are unbalanced, then I call it as an unbalanced 3-phase system. As I told you, for a 3-storied building, in the first floor I have connected all the loads to one phase, second floor to the other phase, third floor to the third phase. Okay. Third floor I have 2 ACs, ground floor no AC, right. So therefore what happens, the load is not balanced in the 3 floors, but still I am taking a 3-phase supply. So therefore what happens, the load in each phase is not balanced, so that house where I have 3 floors with different amount of power drawing capacity in each floor represents an unbalanced system. Okay. So here I just mentioned, in a residential colony, one set of houses constituting load L1 is provided electric supply from R phase, a common point that becomes a single phase supply. When I take a supply from start and this finish point, the common point, I am just tapping only this, therefore it is called as a single phase supply. Okay. Second house constituting load L2 from phase Y to common phase, that means the second house is connected to Y phase, third house is connected to B phase. Because the loads are different, each house is drawing different power, therefore it becomes a unbalanced. Okay. We try to make the domestic load a balanced, but practically it is not possible to balance. Okay. So because of this unbalance, I call the load as a unbalanced 3-phase system, but the supply is balanced. Okay. Now here is an example here. I have taken a 3-phase system and I am connecting a domestic load. This domestic load is star connected, where L1, L2, L3, fine. This is what you have, there is no neutral point here. Okay. A neutral point is there, but that I have not shown here actually. This point will be connected to the neutral of the supply, right, neutral of the supply, the 4th wire. L1 it is R phase, L2 B phase, okay, L2 Y phase, L3 B phase, right. This is also possible, the 4th wire is not necessary. When you connect a 4th wire, there will be a current flow here, otherwise you apply Kirchhoff's current law, IL1 plus IL2 plus IL3, all currents are meeting here, so the sum is 0, fine. So now to the same 3-phase supply I am connecting a industrial load, where in industry most of the load will be 3-phase load induction motor, of course the single phasing also will be there. So you can consider this diagram what I have shown as an industry also, where I will be connecting the single phase loads across like this and 3-phase load a motor like this. Okay. Now this is up to motor it is balanced, but this is not balanced, therefore it is an unbalanced system. See, 4-wire 3-phase system, voltage system, it is flexible, used in distribution of electrical power to domestic and industrial and other consumers. The domestic and other single phase loads are connected between phase and a neutral. 3-phase loads and other loads needing higher voltages are connected between the lines. Okay. With respect to supply, with respect to 3-phase loads, the system is balanced. But when I am introducing into the same systems between the R phase and the neutral, the single phase loads, it becomes the entire system, complete system becomes an unbalanced system. Okay. So, this is an example for an unbalanced system. I have L1, L2, L3, 3-phase. Here the line conductors are there. To this point, I can connect a 3-phase balanced load. But because this is unbalanced, okay, the total system becomes an unbalanced one. But the induction motor, this 3-phase point of view, okay, if you connect any 3-phase balanced load here, it will be balanced only with respect to the 3-phase supply. The entire system will becomes unbalanced because of this presence of these conductors. Okay. So, this delta connection and all we will see in the next session. Thank you.